We're really excited to talk about how you can fine tune a model with 10 rows of original seed data that outperforms GPT-4. Um, I'm going to go through a few logistics on this next slide, and then we're going to do some introductions and dive into the content. We have a packed agenda, so I want to just jump right in. So a few housekeeping items. All the lines are muted right now, but we do have a chat you'll see on the right side of your screen. It's an open chat, so everyone go ahead and say hi, say where you're dialing in from. We get a pretty global audience on these usually. Love to see where everyone's coming in from. Um, but feel free to ask any questions in that chat. We have some teammates who are in there, trying to answer things live as they come up. Um, I'll probably say this 10 more times during the webinar, but we are recording it and we'll be posting it on YouTube and sharing it through email afterwards, later today. We also, I'm just pushing these live. You'll see on the right-hand side of the screen, we have some polling questions. We love to, I'm just pushing these live now. We use these polling questions to get a read on what our audience is doing, what they're building, what they're interested in. In no small part, that's one factor that helped drive the topic for today's webinar, as you'll see in a little bit. So feel free to please answer those. It's really helpful for us. The answers are anonymously shared with the group, so you can kind of see, get a feel for where other people are and kind of what other issues other teams are facing. I'm also just pushing a PDF of the slides so that you can have a copy of the slides for yourself. And yeah, I think the last thing, we will have time at the end for a Q&A that we'll be going through. And then if you like what you're seeing today from the demo, you can get started with Predabase for free. We have a free trial. It comes with $25 of credits for you to use for fine tuning and serving. It's a 30-day trial. So give that a shot if you're interested in what you're seeing. And with that, I'll do some introductions on this next slide. We have a great set of speakers today. We have Arnav and Timothy. Arnav is the team lead for our ML team, and Timothy is an ML engineer on that team. So they have been really cooking up a storm for today, and I'm going to turn it over to Arnav now. Thanks.
Thanks, Will. All right, yeah, great to see everyone here. Hopefully you'll find this fairly interesting. And yeah, looking forward to seeing people's questions and interactions over the chat. So I kind of wanted to start today by showing you a comparison of the average performance of different open source and closed source models on 30 different tasks that we've benchmarked. And what you'll notice shouldn't be surprising to you if you've used both of these groups of LLMs. Closed source models like GPT-4, GPT-3.5 Turbo, 4.0, 4.0 Mini always outperform, almost consistently, not always, but almost consistently outperform open source models out of the box. And that's what makes them a popular way of getting started with LLMs in production. However, the story that's less clear or less known to most is that the things change when you start fine-tuning these open source models. So this chart shows the average performance of open source models after fine-tuning. And the blue bars are the base model performance numbers from the previous slide, while the red bars are the improvement or the average lift in performance post fine-tuning. And this is the average performance over those same 30 tasks. And you'll see that the models here are ranked from worst to best. And we see that all fine-tuned models are better than GPT-4 for the most part. And what's really interesting is is that all the OpenAI models that were on the right side of the chart previously have moved to the left, except for GPT-4, which seems to beat like the Gemma suite of models from Google on those tasks, but loses pretty much a lot of smaller models, most notably Phi-2, which is significantly smaller than the size of GPT-4. To give you a bit of an insight, of like what these tasks look like, there are things like SQL generation, named entity extraction, question answering, And what we've seen is that consistently, when we fine-tune all of these open source models, in a majority of cases, the fine-tuned model outperforms a closed source model on the same task. And the thing that's really important to equally call out is that because these models are open source and they're small, they're about 250 times smaller than something like GPT-4. And what that means for you is that beyond just the quality aspect, your inference costs go down significantly for the same number of generated tokens. And you're also able to achieve much higher throughput because the cost of generating a single token is much lower since these models are smaller. So really, the question that this brings up for me is that open source models have high. We can see that there's this promise of high quality, lower cost for inference, but the question really is, why aren't more teams fine-tuning? So to understand this better ourselves, we decided, as you're seeing in demo today, we decided to survey all of our webinar attendees over the last year. And a majority of our webinar attendees did confirm that they weren't actively fine-tuning any LLMs, closed or open source. And in most cases, we're using closed source models along with prompt engineering. And to dig into why they weren't, why there was a majority that weren't even thinking about fine-tuning or looking into fine-tuning, we saw that an overwhelming majority of all of you actually said that the biggest barrier was access to data for fine-tuning LLMs. Well, what if you could outperform prompt engineering using fine-tuning without collecting thousands and thousands of rows? We found that this is actually possible by using LLMs to generate synthetic data and using strong LLMs to do so. To give you a glimpse of just what performance looks like, and we'll show you much more of this throughout the rest of the webinar, we've seen that all you need to get started is between 10 and 25 demonstrations of the task that you want the LLM to perform. With only 10 rows of real data, we fine-tuned a Llama-3 model on a combination of the real data and the synthetic data. And we saw that it outperforms 10-shot GPT-4o in the same task. And this task is like a common sense inference task, which we'll talk about through the rest of this webinar. And so it is actually possible. And what you see in the chart on the left is actually, so 10-shot Llama-3, 10-shot GPT-4o, which does significantly better than Llama-3 out of the box. So consistent with the observations in the original chart that I showed you. And then finally, post fine-tuning with synthetic data, using just 10 seed examples at the beginning, we were able to beat GPT-4o at a significantly, by quite a big margin and at a significantly cheaper cost. And beyond just improving, and so, when should teams really consider synthetic data? Beyond just improving quality for open source models from fine-tuning, synthetic data is very useful for teams and organizations where, there's three big reasons where data is insufficient. So this could be because you have a new use case, there's data quality issues, or, there's big performance gaps with, prompting. Data is inaccessible. Usually it's because of organizational barriers between the teams that are doing ML and the teams that actually have all the data, so usually data engineering teams. And then the third big reason is if the data you want to use is private. So customer data with personally identifiable information, things of that sort. Synthetic data is sort of helps with all of these scenarios in particular. So with that, I'd like to spend some time walking you through a few synthetic data generation methods. But the difference is that if you've read literature on this, most literature is around general purpose dataset generation for pre-training. But what I want to focus on today is on methods to generate narrow task-specific data, because that is what most organizations actually want to put into production. To help understand the strengths and weaknesses of some of these methods, we're going to use two data sets today. The first on the left is the HelloSwag dataset, which is a common sense completion task that is very easy for humans to do, but surprisingly difficult for machine learning models to get right, since it involves contextual understanding and some reasoning ability. The second is Corona NLP. It's a Twitter sentiment, tweet sentiment classification task, which has 5 classes. and 5 possible labels. So I have examples of these here, and you'll continue to see more as we walk through the webinar. If we pause and think about the easiest thing we can try to generate synthetic data, maybe you've tried this in the past. It's this method that we're calling examples in, examples out. And the basic idea is that you can take 10 seed examples, pass them into a prompt in sort of K-short fashion, give it some task-specific context. Maybe in the HelloSpag case, you might actually describe the task, give it some examples, as mentioned earlier, and you ask the model to generate one or more synthetic examples at the end. And often, one of the challenges with synthetic data creation is encouraging the model to produce diverse examples. And the easiest way to get around that we can try is to actually vary the temperature that we use at generation time. If you're not familiar with temperature, it's a parameter that it's a generation time parameter that you can use to vary essentially the determinism of the model. So at lower temperature, it's more deterministic, but as you increase temperatures, you shift the distribution, and it allows LLMs to get more creative in their output. And so this is the first thing that we tried, felt like the easiest place to start. And while this method is simple, it's fast, and has a low cost because you can generate multiple examples with the same LLM call, we saw that the biggest weakness of the simple approach is this notion of context averaging. And what this means is what we saw is that the LLM tries to pick up on nuances and topics from all the seed examples that we pass in the K-short fashion. And what that does is it sort of creates this homogeneous synthetic data set that both lacks diversity and the nuances from any single example. And the interesting thing is that that happens even with varied temperature values. Some other weaknesses that we noticed are that while it tends to generally understand the task itself, it often produces very simple examples that can be a bit ambiguous and miss important details. So essentially, even if you were able to create these examples through this algorithm, post fine-tuning, you might find that the model doesn't perform very well on your evaluation set or your golden test set because of the ambiguity or the simpleness of these examples. Just to illustrate what that looks like, I picked some examples from our initial experimentation with this method on the HelloSpag dataset. So the structure of the HelloSpag dataset, which maybe I should have clarified earlier, is that it contains a prompt. So the prompt has sort of like a sentence with some contextual details, and at the end it has 4 possible endings, indexed with 0, 1, 2, or 3, and the goal for the model is to pick the right index. So if you look at the example on the left produced by this method, you'll see that it's clear, it's contextually appropriate, there's no real ambiguity, and it's pretty clear that if a group of tourists are taking pictures in front of a famous landmark, they might ask someone to take a group photo. That is the most logical ending. So this is a good example. However, on the right side, it's an example that is actually a very poor example, and poor examples tend to hurt LLM performance quite a bit. You'll see that in the second case, it's a very simple prompt. A couple walks into a busy restaurant, and there's 4 possible endings. But when you observe this example, you'll notice that choices 0 and choice 2 are both equally valid. It's more context dependent. There's missing context in the initial sentence. And so what this really hints is that this method of generating synthetic data wasn't really able to completely grasp the general idea of the task, which is to generate one single non-ambiguous and contextually valid completion from the prompt and the endings. So to solve for maybe some of these limitations, right? What if we were to flip the script 180 degrees? What if we just passed in one seed example at a time and ask it to generate one example back with similar characteristics, right? And this was our new hypothesis that we wanted to sort of validate. And what we can do is we can just keep looping over these seed examples iteratively until we generate the desired amount of synthetic data. And once again, just to also continue playing around with it, we decided to vary temperature to improve diversity. And in the good news, and I'll show you this through examples once again, is that this slight change from using all seed examples at one time to iteratively using single seed examples makes a big difference in quality. We saw much higher specificity, and I'll tell you what that means in a moment, and a higher percentage of valid examples. So these examples, because the idea is that because it was able to focus on one example at a time, it was able to understand those tasks, I guess that data specific nuance and characteristic, and then utilize that to create a very similar example. So it was very specific in what it does. And the examples themselves, as you'll see in a moment, are a lot richer because of the lack of the context averaging phenomenon that I had mentioned earlier. And these examples are much more in line with the properties of the seed dataset difficulty-wise. So you won't find as much of a skew in performance if you were to use this method to generate synthetic data, train a model, and then evaluate it. However, one of the big issues is that it may still miss some general task level nuances because it now looks at only one example at a time. And in some instances, it can even cause distribution shift issues, such as in the case of classification data sets. Just to show you what this looks like, similar to method one, here are some examples that were produced for method two for the same HelloSwag data set. What you'll see on the left is much more detailed or contextually, I guess, it is a much more richer example, has several contextual elements, and there's actually a very valid completion here that's non-ambiguous. So right on the money with the seed data sets, seed examples that we passed into this algorithm. On the right, what you'll see is that the synthetic example is actually not a valid example. And if you take a moment to look at why, you'll see that the initial prompt, the last sentence of the initial prompt ends on a period, which means that the completion needs to start with a capital letter and not a verb, which is sort of what's happening here. Right, and if you think about what might have happened beneath the surface, right, because we're trying to learn and solve for weaknesses iteratively, it was probably this example on the right was probably created from a seed example where the sentence ended with the period, but did actually have grammatically correct completion. So the seed example probably did, but because the method only focuses on one example at a time instead of 10 examples to get like the full context, it was not able to grasp the task at hand. Right, so that's unfortunately a trade-off that we've made by going a complete 180 degrees. The second thing that I want to show you is this idea of data distribution shift, and it's particularly important in classification style tasks that you might want to fine-tune for. Right, so let's say, so what we did as an example is we took a 25-row seed data set for the Corona NLP data set, which if you remember is a multi-class classification data set with 5 classes. And what we did is that in the seed data set, we ensured equal representation for each of the 5 classes. However, when we took the seed examples and asked it to generate 25 new synthetic examples, we noticed that the distribution of the classes was not maintained and was actually heavily skewed towards 2 of these classes, extremely positive and negative. This is probably likely because the LLM only got to see one example at a time. And it also tends to favor certain classes like extremely positive over positive because it doesn't know how to differentiate between the two. And it might have learned that if it got all case shots in one go. Some more trade-offs. I think we've made an improvement from method 1 to method 2, where we're generating higher quality examples, but just clearly it's still falling short in a couple of ways. So if you want to improve on this further, we decided to try a third hypothesis, which is called the single pass method. So just once again, to reiterate, from method 2, we can see that we saw that using a single example definitely helps generate richer examples. But one of the big weak points was the lack of context that the model had, which it lost because which it had initially when we used case shots. So to solve for this challenge, we added this thing called the task inference prompt. And what the idea here is that we take the seed examples, pass it through a task inference prompt, and generate some inferred task context. So it has various details about the task, the domain, many other characteristics I'll talk about in a moment. And the idea is that once we have this task from the larger set, we can use this and pass it into subsequent calls when we're generating data. The other aspect that we know about LLMs generally, right, is that um, they perform the best when you break down problems into small sub problems that can easily be solved for. One idea that people normally think about is or that came about last year was this idea of chain of thought reasoning and tree of thought reasoning, things like that, where you ask it to reason about a process and then um, you know answer the question based on that reasoning. But the core idea there is not so much like the process of that, but the idea that you can break down a problem into smaller solvable problems and then join the answer together. So a simple thing we can try is, instead of generating both the prompt and completion in one go, which is what we were doing before, we can actually break down that into two sequential calls, where we first generate the prompt from the seed example and the inferred task context, and then we generate a completion using the seed example, the synthetic prompt, and the inferred context. And this idea of using like an LLM to mimic or perform multiple roles, right? We're asking to generate context and generate a prompt and generate a completion, which are all different tasks in this chained manner. You might have heard of it as agents, and here we're going to leverage three different agents. To show you what the task inference piece looks like, just diving further in, we try and infer various attributes such as domain, structure, tone, format, intended use, target audience, and things of that nature. And what's really fascinating about LLMs is that they're very good at this kind of inference from a large amount of data. In fact, I would say that they're quite on par or on, or maybe even better at in the way that they describe patterns and data. And so we decided to write this prompt that just infers it from the data set itself, using all of these different attributes to produce an output. To give you an example of this exact task inference prompt in action, here's an example of the inferred context for the HelloSwag dataset. There's a lot of text here, but I've highlighted 5 things from top to bottom that I wanted to call out that I think are very interesting to note. That right. The first is that it was able to understand that the domain of the task spans across multiple topics. So there's no specific domain, but it's this idea that, remember, the HelloSwag dataset has these prompts and completions, but the topics of those don't actually really matter. So it's able to understand that. The second is that it's able to identify that the structure of the prompt, identify the structure of the prompt column and find these repetitive patterns, which is the 3 hashtag signs and then the endings colon followed by a list of possible continuations. The third is that it was able to correctly identify the goal of the task, right? It understands that we want to select the correct continuation based on the context provided in the prompt. The fourth is that it understands that all the synthetic examples, this is paragraph 3, all the synthetic examples the formatting of the examples must be preserved across the synthetic examples that are generated. So you must use the 3 pound signs, the endings colon, like the bulleted list, index list. And the last is also that it acknowledges the ambiguity in the domain. So it doesn't understand this as like medicine or something else, but it understands that there's no fixed domain because of varied scenarios, but it also lists some examples of scenarios that it's seen. So all of this happens with the prompt, and then this is passed forward to all of the examples. And what's really cool about this is that we're not using, so remember, the problem was that when we used 10 examples and passed it directly, we saw context averaging and a lack of sort of this like homogeneity in the data set that was produced. But by doing the context inference, we're not passing the examples, but we're passing the idea of passing case shots is to give the model context, but we're basically trying to infer that context and pass it forward instead without influencing the model too much while generating synthetic data by looking at those same seed examples. So significantly enhanced contextual understanding without dilution, which is a big win, and definitely solves one of the problems. And because the context is the same across all examples, and it is very detailed. I only showed you a snippet of the total context where we derive. There's higher consistency in the quality of the samples. And the third thing I wanted to emphasize is the idea of like a balance between specificity and diversity. So specificity is this idea that we want an LLM to focus on one example at a time to generate a new example. So it doesn't, trying to break down a problem into a very simple problem. But then we want to also encourage diversity, but keep it grounded. And that's where the overall inferred context comes in. Um, However, on the weaknesses side, there are certainly this method is not perfect. One of the things that is very important is the quality of the inferred context is largely dependent on the seed examples. And Tim will discuss this pretty soon. Uh, so you'll understand the challenges we went through there as well. And the second is that this method still suffers from a data set distribution shift challenge, but it's not as bad as in method two because we have there's a lot that we can do in the inferred task context that grounded in understanding it's a classification task with labels and things of that nature. So to further solve for the limitations of this approach, there's a fourth method that we can explore that's called mixture of agents. And the algorithm is divided into improvements in two of the key parts that are weak in the single pass approach, right? It's the context inference piece. There's something more that's left to be desired there, and the generation aspect itself. So um, so while the generation, so I'm going to divide this into two separate slides. The first is, as we discussed, the context inference piece. So what we do know is the task inference, the context inference is working really well. We tried this on a really wide variety of tasks. Um, but the part that's missing is this distribution shift. And one way to solve for this is actually by calculating some data set statistics. So you can do things like data set imbalance, like prompt to completion ratio, completion to prompt ratio, length distributions, lots of clever things that can be inferred. And you can actually now pass in this task context and data set statistics very smartly into subsequent prompts at generation time. And the way to think about data set statistics in particular for classification is that it's not exactly giving the model a probability distribution to sample the completion, but it's sort of influencing its understanding of the larger picture, which is that some labels are less likely, so think twice before picking it. So that's one aspect of the mixture of agents approach. And the second is, how do we actually use this and take it forward? So we're still going to keep one seed example at a time. We now have inferred context, and we have our data set statistics. And the mixture of agents generation phase involves three big steps. The first is the candidate generation phase. So the idea is that we're going to pass in the seed example, the inferred context, and data set statistics into two consecutive prompts. The first is generating the prompt candidates, and the second is generating completion candidates. But the difference is that this time we won't just generate one candidate. We will generate maybe one, n number of candidates, say 3 or 5 or 7 or 10, can be an arbitrary number. And this will give us, n prompt completion pairs to consider in one go. And we still split the prompt and completion separately because we learned that works well from the single pass algorithm. The second phase of mixture of agents is the self-analysis via chain of thought reasoning. And the idea is that we want to critique the examples produced. So we know that we might not generate everything perfectly because we're only looking at one example at a time with context. Sometimes we might miss some very simple things. So the idea is that if we were to self-reflect on the examples produced, the original examples in the context, and some data set statistics, we can try and be more objective about how well we did. And so we ask the LLM to reflect on itself. We give it some good list of criteria to consider. But the general gist of it is that we want to give it both positive and negative reinforcement. So tell it what it's doing well, tell it what it's not doing well, and do this for each of those synthetic candidates that we produced, right? And this will give us a set of critiques for each of these examples. You can imagine, like a dictionary that says positive feedback and constructive criticism, right? Or it could be some other structure. And finally, phase 3 is this phase of refinement and synthesis. And the idea is that now we can take all of this information, so seed example, inferred context, data set statistics, the candidates we generate, and the critique for the candidates, and then actually ask it to generate one high quality synthetic example using all of this information. And so this is, again, another prompt that we're going to push all of this data through to get its final example. And the goal is to generate one high quality, non-ambiguous, clear, detailed example that we can then use for fine tuning. And what's really incredible about this approach is that it's not technically a novel idea. We've made a lot of improvements to ideas presented elsewhere, but it really takes this idea of breaking down problems into smaller subproblems by combining these proposers, so the generators, with critiquers and aggregators for stronger performance. All right, and it's really, really useful for data sets that require, that are very detailed or require multi-step reasoning. It's really good where there's a lot of bias in the seed data sets because it tries to reduce that or keep it depending on the desired behavior. And it helps improve accuracy through the reflection. However, on the weaknesses side, I think the biggest drawbacks that we've seen is that it is slow to produce because there's a chaining of many calls, and it's very expensive. That being said, a lot of people have proposed this mixture of agent sort of approach for real-time inference systems, which is not at all, it's very hard to put that in production, both from a cost perspective, but also from a latency perspective, because you have to change these calls sequentially. However, we can take the advantages of that approach, right? Create a synthetic data set by paying that cost upfront, and then fine-tune our model so that it understands these things, and then we don't have to do these chaining of calls. And so we're taking the idea from inference, we're bringing it to training through the synthetic data approach. And just to maybe finish this out, here's an example from this final method. And the thing I wanted to call out is earlier in one of the methods, when there was a period at the end of the context, it got all the ending suggestions wrong. But because of the chain of thought reflection process, it was able to critique itself, say that it was grammatically incorrect. Then it was able to say how it should fix things, and it did actually generate one high quality synthetic example from that same seed example at the end. And so this is a rough overview of some of the methods that we've tried, things that we've learned. And I'm going to hand it over to Tim to actually walk you through some of our results and our experiments with these different approaches.
Cool. Thanks, Arnav. Let me start sharing my screen here. Everyone can see my stuff?
Yeah.
Cool. Sounds good. So I'm now going to go over a little bit of our experiment overview. I know some of you in the chat are curious as to how we did some of this stuff, which models we used, so on and so forth. So I'm just going to go over that really quick. So here you can see what our general workflow looks like. We start off with our base data. And so we'll send this seed data into what we are calling our predibase augment function for our synthetic data generation. This new augment function allows us to take this base data and send it to a model like, for instance, GPT-4. For us, we use GPT-4 Turbo for our experiments. And we send in 10, 25, 100 examples. However many you have is generally how much we would recommend you use in production. We then generated 1,000 samples, generally, for our synthetic data, applied a bit of post-processing just to make sure that everything was consistently processed, and then fine-tuned in Predibase. On the other side, we also applied k-shot formatting to our seed data. So again, 10 seed, 25 seed examples goes in. We do, let's say, 25-shot formatting through OpenAI. And the model we compared against here was GPT-4o. It ran these samples through, and then we evaluated using our evaluation harness, which I'll go through just really quickly later on. As for the data, like Arnav said, we used Corona NLP and HelloSwag as our two data sets. We wanted to select data sets that could reflect real-world use cases, so in this case, sentiment detection and sentence completion, but also had objective metric functions, or specifically not rouge. We wanted something that was very, very much objective and unbiased. These two datasets were also part of our previous Loreland work, so we had prior familiarity with them, which is why we wanted to stick with these two. I mentioned our evaluation harness, which allows for fast parallelized querying of our REST API. So there's a solid amount of retry logic and some self-tuning delays just to help stay under rate limits. It's a very, very nice tool. We recommend you try it yourself. There's a QR code on the screen if you wanted to check that out. I'll just leave that up for a few more seconds for anyone who wants to take a look. Open source, it's on GitHub. But moving on to our actual synthetic data. We had to start by choosing our seed samples. This is not something that you would usually do in production because if you have the data already, why not use all of it? For us, this is our experimental setup just to see what we could do with this. Our initial attempt was an arbitrary selection of seeds. So we picked the first K in our data set. And what resulted was occasional label mismatching or ambiguity in our prompts. So what you can see on the screen is an example from a synthetic data example of Corona NLP, where the sentiment is negative, but the prompt is a little ambiguous. We can't quite tell definitively that it's a negative data sample. So we weren't quite happy with this approach, and so we decided to go with what we thought was the clear next step, which is to handpick our samples. Hence, the results got better. After handpicking our samples, we ended up seeing more consistency between our prompts and our completions, and we saw clear delineations between our classes. So everything became a lot more distinct. As you can see on the example here on the screen, this became a much more clear, positive example. And we also saw that our overall results and performance got noticeably stronger, which I'll show a little bit further on. So a few key factors that we looked at when handpicking our samples, Arnav alluded to this earlier with our dataset statistics, but we wanted to keep in mind dataset balance and imbalance. We wanted to make sure that we had completion lengths that were indicative of the actual completion length in the dataset. Completion quality was correct. We had a lot of variety in the topics of the prompts that we selected, and the grammatical structure of the prompts also were decently varied and grammatically correct. With these 5 factors in mind, we were able to usually select a good number of hand-selected samples that increased our performance. And now I think the parts that many of you have been waiting for, I'm going to dive a little bit into what our results look like. Recall this data point. This was a really exciting finding for us when we saw that our fine-tuned llama model was beating GPT-4 when it was fine-tuned with a synthetic data sets using only 10 seed samples. Obviously, though, we needed to expand upon our findings further. But before I even get into performance, I want to take a moment, step back, and just lay a few assumptions out here, right? Let's say you generate 1,000 synthetic samples using GPT-4 Turbo, use MOA prompting for the highest quality. You have prompts that are about 1,500 tokens long on average, and let's say the completions are 800 tokens long due to all the internal prompting. For inference, you decide to do the same test that we are. So you fine-tune a 7 billion parameter model. Inference takes, let's say, a high 5 seconds per sample. That's generally going to be much slower than what we would have, but let's do this for the sake of argument. You run this inference on an A100 in Predabase. Then you query GPT-4 in production. Your prompts are about 1,000 tokens long on average. Your completion is about 50 tokens long on average. I think those are some fairly reasonable assumptions. If we were to use those, we arrive at the cost graph that you see here. So that x-axis is the number of requests per day. The y-axis is your cost in USD. And then each of those lines represents a difference method. So blue, red, yellow, green, those are increasing order of K shots in prompting GPT-4 whereas that bottom orange line is how much it would cost you to use a fine-tuned Predabase adapter. You're paying $367 to generate the data and then query the Predabase adapter. Whereas if you're passing in 100 examples every time to GPT-4 you're going to end up racking up a bill of over $5,000 a day, assuming you do only 20,000 requests a day. That's more than a 14 times difference. Clearly, Predabase is saving quite a bit of money as opposed to using GPT-4 or other large models in production. On the performance side, there were some really promising things we saw here as well. Note that initially, GPT-4o is winning in terms of performance. But once we hit around 80 ground truth examples, fine-tuning starts taking the lead. After that point, fine-tuning only gets stronger while K-shot prompting plateaus. Of course, there's going to be an upper limit at some point, but fine-tuning is increasing steadily. In fact, anything at, let's say, 1,000 ground truth examples and after is basically impossible for K-shot prompting due to context window limits. You can see here, this is our Corona NLP adapter. That inflection point is even further to the left. That inflection point past which fine-tuning will outperform K-shot prompting is generally task-specific. It will generally shift further to the right as the complexity of the task increases. However, once the inflection point has been hit, fine-tuned models do tend to perform better on complex tasks than open source ones, as evidenced by our previous LoRaWAN work. So there's that trade-off there. If you have a lot of data to use, your complex task adapters will do really quite well. If you have a limited amount of data, it'll still do fine. It will be just slightly less lift. And now I'm going to do a quick live demo of this Predibase augment function. So let me start here. One moment. Let me make sure I have the right screen here. Oops, that's not. Sorry, folks, give me one moment here. Cool. If you guys can see my screen here, we have our 25 hand-selected Hella Swag data samples. You can see what they look like. We have our prompt here, and then we have our endings. Completions over here. We have our train set. This is for our train set. And all I'm going to do is I'll hit augment dataset. We can provide a name, and just to help you keep track of what your datasets are. We have our augmentation strategy, which is mixture of agents or single pass. So this is method 4 and method 3 that Arnav showed earlier. You can pick any of these models as our teacher model. I'm not going to pass in my OpenAI key right now, but you pass in your OpenAI key, and then you can select how many samples you wish to generate. Also, this is where you can pass in the task context. The inferred context is usually what we would provide here. But if you'd like to pass something custom in here, we'll do it as well. And what this will give us is this. This is our 1,000 synthetics based off our 25 seed examples. So what you can see here is, for instance, a tutorial on how to create a Dutch braid. And it shows you how, and these endings are provided here, all fairly consistent. We're generally pretty happy with the quality of these results. And so once you do this, you can just start fine-tuning on this data set. And so I will go back to the slides. So with each one of our webinars, we like to give a few last takeaways for everyone to walk away with. I know that we just had a lot of content for you there, so we want you to walk away at least with a few really key messages from us. Number one, the quality of your base data is key. When we went from arbitrarily selected 10 samples to hand-picked samples, the quality of our synthetically generated data went up considerably. So even if you have a limited amount of data, make sure it's high quality. Number two, quantity still matters. If you remember the charts that we showed, as you increase the number of ground truth samples you have, the better you'll do. Synthetic data generation is just there to help even the playing field a little bit more. And finally, fine-tuning will beat out K-shot prompting eventually. This ties into the quantity mattering point, but there will be an inflection point at which your fine-tuned models will start to do better. However, the largest takeaway that we want for you to walk away with is, with just a few rows of data, you can reach GPT-4 levels of performance at a fraction of the cost. Overall, the small language model challenge still continues to be a pretty big task. Training and serving small, cost-effective, performant models is not an easy thing to do. One, data for fine-tuning is often still a bottleneck. Lots of tools and techniques are out there for you to learn about, to master. And of course, the infrastructure is hard to manage and it can be quite expensive. Here at Predabase, however, we try to solve these problems for you. We have an intuitive workflow now for synthetic data generation with our new augment function. We have easy, efficient fine-tuning with over 50 optimizations that we handle for you. And with Lorax, we provide powerful serverless, auto-scaling, multi-LoRa serving. Thank you guys for coming to our presentation, and I'd like to open up the floor for Q&A. Thank you.
Tim and Arnav, thank you so much. That was wonderful. I learned something every time you guys run a webinar for us. We have some great questions. Really appreciate the lively chat, everybody. That's been wonderful. One question from Andrew. Is there a means to evaluate the 1,000 synthetic data points to, say, choose the best 500 for fine-tuning? Or how would you approach that?
To evaluate the 1,000 that say choose the best 500 fine-tuning. Wow, that's a hard one. If you have the time, obviously, manual selection is going to be optimal, I would say, for human. 1,000 is a lot. My next solution would be to pass in. What you could do is pass in 500 examples into a model like GPT-4, and then pass in another candidate example, and basically tell GPT-4, hey, I have 500 examples, and I have this one extra sample that I want you to judge. Tell me which sample would I switch out, or would I just leave out this new example completely? And you can do it that way and iterate until you have your 500 examples. But I would say handpicking is still going to be your best bet here.
Thank you, Timothy. Let's see. Another one, this is kind of related. What would you say makes a sample high quality? Can we do anything up front to confirm if it is high enough quality for how little data we have?
As I showed in a previous slide, let me see if I can get back to it really quick. This is going to take just a moment. These are the factors that we took a look at when confirming that a sample is high quality. It's kind of hard to tell in a vacuum. So what we do is we have to compare our samples to other samples that we have. It's the overall, keep in mind that it's the overall quality of the data set that you have to take a look at. So if your data set's fundamentally imbalanced, that's going to be a problem. If you have all of your samples looking very, very similar to each other, that's also going to be a problem because your model is not going to be able to learn enough. So I'd say a sample is high quality when, if compared to other parts of the data set, it adds a noticeable amount of variety in the prompt. And of course, the completion has to be like logically sound. Like you can't have like an obviously extremely negative prompt and then have the completion label be positive or something like that. That's generally the stuff that we have to take a look at for high quality samples.
Great, thank you. Let's see. This is one that I imagine you'll have a lot of thoughts on. Thank you, Nick. What are your thoughts on the base model? And this is
Is
actually
this-
something we
Is
have.
this a base model for fine-tuning or for synthetic data generation or both?
Fair
I
question.
think we can probably answer all of those, right?
Yeah, I have a take, and it's based on things that I've tried and things that I've seen across different forums. In general, both Llama 3.1 and Qwen2 are very strong base models, some of the leading ones today. In particular, if you're looking for training, Llama 3 seems to outperform Qwen2 in more cases than not. But where Qwen2 really shines is its 72 billion parameter model, both on fine-tuning as well as on synthetic data generation. So it's a very popular choice for synthetic data. And if you, yeah, but what we also seen is, Llama 3.1 billion seems to just do so well. And even going to larger sizes like 70 billion doesn't give you a significant enough lift to justify the cost of inference and throughput reduction. Not sure, Tim, if there's anything else you want to add, but that's what I've seen so far.
No, I think that more or less covers what I would say about the base models. Like fundamentally, like Llama 3.1 billion is not going to be a specialist model. That's why we fine tune. And so I wouldn't necessarily be comparing base Llama 3.1 to like GPT-4.
Yeah, I also see Nick asked a follow-up, which was instruct versus non-instruct. Again, we'll defer to Tim, but what I've seen is that the base model post fine-tuning seems to generally outperform the instruction tune version post fine-tuning. In a majority of cases, I think that there's a big distribution shift with regular instruction, like post pre-training instruction tuning that a lot of these base models go through. But I'd say also it's heavily dependent on what data sets we use to do the instruction tuning. So not yours, but the base model itself. If it's very aligned with, for example, the kind of tasks that you have, usually like things like science, math, reasoning that require strong reasoning, I'd say instruct models tend to beat base models. But otherwise, like base models plus fine tuning tend to do better. Tim, anything to add there?
Yeah, our lower land results tend to show that, of course, not fine-tuned, the instruct models are far stronger. But fine-tuning closes that gap really, really considerably in that once we get to the end of it, oftentimes it's almost indistinguishable sometimes between what the instruct model and the base model do. But to Arnav's point, yeah, actually the base model does end up doing sometimes slightly better, sometimes noticeably better than the instruct model, depending on the task. And I think Arnav makes a really good point that it does depend fairly heavily on what the instruct model had in its original training, as opposed to the base model.
Wonderful. Thank you. All right, here's one. Can you elaborate more on how you leverage the dataset statistics to create synthetic data?
Yeah, absolutely. So there's a few different things that we do. The first is, I think the most important is figuring out dataset imbalance, which is how unique are the candidate prompts, the seed prompts and the seed completions. And from that, we can actually figure out some pretty clever things. For example, if the data set is very skewed, let's say mostly unique prompts, but hardly any unique completions, we can infer that this is actually a classification task. And if that is the case, then we can use so there's two things we can do, one of which we do, one of which we will be doing soon. There's two things we can do. One, we can smartly pass in, like extract class labels at that point and pass that into the completion part of the generation so that we constrain the breadth of choices. Because one of the challenges with classification generation, for example, is that if you have a fairly wordy label, let's say it has multiple words in it, sometimes the synthetic data will, with naive methods, will pick like a few words from it. Let's say like you have, like in financial services, you have like a credit or debit check. It might pick like credit check or debit check, but you wanted to pick that one as the full thing as a label, so you can add that in as context. The other part is that during generation, what I found is that by passing some of, it's basically, okay, so maybe to simplify, you can create some simple statistics, then create more interesting statistics based on whether it's a classification or generation task. and then smartly use that in your prompts to help not so much at generation time, so generation time for classification, but in particular at critique time. Because what you can say is, hey, you've got all of these different candidates because we generate n of them in the mixture of agents sort of approach. Like, are these even falling in the distribution of the original data set? And if not, then I think you need to take a look at the labels again. So that's the way it's used. It sort of helps shift the distribution closer. It's not perfect. There's still work to be done there, but that's the high level idea of how it's used. So it's task inference and then grounding the completions to stay within the distribution as much as possible, both for generation and classification tasks.
Wonderful, thank you. We are running up on time, so I'm going to try to get through just a couple of last ones. Let's see, here is one. We love this question. What kind of tasks are suitable for fine-tuning with a small base model? Because of its limited ability to generate as a general language model, there would be some cases that do not do well for fine-tuning. What do you guys think about that?
I'll take this one. So there are some tasks that we've noticed are definitely harder for small models. In particular, coding. That's one that basically consistently the large open source models, large closed source models are going to do really, really well on, as opposed to smaller models, even after fine tuning, just because we don't have that quantity of data to work with. But any kind of data that, any kind of task that actually has really nuanced or specific formatting or any really, really specific details that the model has to pay attention to, fine tuning does noticeably better, just because the model is able to pick up a lot of those nuances because it's trained to do so, as opposed to like GPT-4, where even if you were to pass in 100 samples, it's not going to be able to pick up on all of the patterns that are involved there.
Yeah.
So actually, Corona NLP ended up being one of those data sets in that some tweets are actually fairly ambiguous in that data set, but the more you fine tune on it, the better and better the model got, just because it was able to just observe all of that nuance and then properly label the data.
Just want to quickly add to that. So yeah, totally agree with what Tim said. Use cases wise, it's everything from custom code generation. So, you have workflow tools, so custom SQL, to structured named entity extraction, to structured generation, forcing it to do like JSON or YAML, classification, and also that's like one type. The only other thing I wanted to call out is there's also this thing called domain adapted continued training or pre-training, and where you can actually inject domain specific knowledge so that the model is more likely to understand those words. Imagine you work at a company that has lots of different tools. You can actually inject knowledge about like your sort of like knowledge-based injection through fine-tuning as opposed to RAG. The one place fine-tuning doesn't do so well is real-time systems where data is constantly being updated like every second. That's because fine-tuning is done ahead of time. That being said, it can still fit into that pipeline by helping, as a post-filter step or as an assistant as part of the overall pipeline, but just not in like, very, very real-time question answering systems.
Thanks, Arnav. All right, I've put in the link to our Discord in the chat again. I know it's been in there a few times, but please, unfortunately, we're out of time. But we really do love picking up conversations in Discord. So feel free to hop in there, answer, ask any other questions that might be top of mind. We'll be putting this recording onto YouTube as soon as we can, hopefully today. And generally, just thank you all so much for the discussion, for the questions, for joining. And thank you to our speakers for walking us through this concept. Thanks so much, everyone. All right, take care, y'all.